On the other, which is basically to say that if we solve the equation du dt equal to f of ut, which is equal to 0, okay, we still should see the same problem. Okay, so why don't we just change that to 0? How about that? How about we change that to 0? So if we change my right-hand side to 0, what do you think? Do you think I should reproduce the same problem? Anybody take a guess? Yes? Exactly. Actually, everything stays 0, right? I mean, if you take a look at u, I mean, it's all 0, right? Here, if I do norm of u, 0, right? Norm of u equal to 0 means every u is 0. There is no way for the norm to be 0 if anything is non-zero. So we actually cannot reproduce the problem if f is equal to 0. Is that really true? Actually, no. We can, what I would say is we can reproduce the same problem when f is equal to 0. We just need to seed it a little bit of non-zeroness into the terms. So for example, if we are going to, let's say after the midpoint, okay? After the midpoint, let's make u1, which is equal to 0, right? Equal to 10 to the minus, what do you want? 300. How about that? Do you think that matters? Nobody would say it matters, right? But let's run it. Okay, we see that it starts with 10 to the minus 300, right? Okay, becomes bigger and bigger, still 10 to the minus 100, 10 to the minus 50, 10 to the plus 35. Now it matters, right? So that's the problem, right? Even if I set the right-hand side to 0, okay, if I make any a little bit of initial perturbation, 10 to the minus 300. Oh, by the way, 10 to the minus 300 is close to the smallest number that can be represented by a double precision floating point in a computer. Okay, that's kind of the most accurate regular number system in a computer. You can have more advanced representation that is more accurate, but it's not supported by the hardware. You have to kind of do software. You have to actually program to get that. So even if you start with 10 to the minus 300, you eventually get to 10 to the plus 300, which is roughly the biggest number you can represent. Afterwards, you get infinity. All right, so here's the problem. Okay, how do we actually figure out that these three, I mean, the problem really has to do with these three numbers, right? Minus 1.5, 3, and minus 2. Somehow, even when this is 0, I got rid of it, right? I start by choosing three numbers that are basically 0, right? Two of them are 0, one is minus 10 to the minus 300. And then I apply the same formula again and again. And after a little bit of while, I get infinity. So what's wrong with these three numbers? How do I know these three numbers are going to get me problems, right? While the midpoint rule is not going to give us any problems. Yeah, what's wrong with these three numbers? Yes?
So I guess if there's like a small error, then that is accessed multiple times throughout the steps. Like if one has a small error, then you see that when you calculate 2 and 3 and 4. So it can like be compounded.
Yes, compound of error is the key, right? So whenever you do a stability analysis, whenever you look at anything that is unstable, there are two ways things can go unstable. One way is what you are saying, like when the error compounds, right? In the first step, you get 1 error. Second step, you get 2 errors. Third step, you get 3 errors. The error just adds up, right?